A very good morning to all of you. So today we will first look at measurement of celestial distances. Just a brief overview. And we talked about estimating intrinsic properties of radio sources or any celestial objects. And we saw how important it was to know the distance to these objects in order to estimate either its luminosity or its intrinsic size, because distance is very fundamental in trying to estimate the physical properties of these objects. So today we will have a brief overview of how we have built up our estimation of distances to celestial objects, okay? And starting from our solar system, and this particular picture is not to scale as you'll usually make out, to the most distant objects in the universe. Today, the most distant objects have a redshift of about 10 or so, and is almost at the edge of the visible universe. So we will go step by step and see how this distances, as often referred to as a cosmic distance ladder, because it's really a rung by rung that one builds it up, has been arrived at over decades and decades of extremely careful and work in recent times. But the history goes back to the Greeks, actually, goes back to ancient times, when people tried to measure not only the size of the Earth, but also distances to the moon, for example. Okay, so direct distance measurement for nearby objects, where trigonometry and geometry have played a major role. Okay, indirect methods use more objects which can be used as standard candles or standard rods. What does that mean? That means that if you know an object has a fixed luminosity, then you can go and determine what its distance is from the observed flux or flux density. Similarly, for a standard rod, if you knew what is the length of the rod, then you can go and estimate its distance by seeing what the angle that the rod subtends. But I must sort of mention over here that when you learn cosmology, you learn different ways of measuring distance, such as the angular diameter distance, which is what a rod will give you as it, for example, a rod could be like a double lobe radio galaxy, which I mentioned earlier. And as that goes further and further away from you, how the angular size changes with distance is given by the angular diameter distance. On the other hand, luminosity, the way the luminosity of an object, the flux density or the flux appears to decrease, will be given by the luminosity distance. But right now we are looking at a very nearby universe. And these different distance measurements are not significantly different for the nearby universe. So to start off with trigonometry and geometry, because that is what played the major role in trying to estimate distances of the nearest objects. So, and in each step, we will see that there are checks and counter checks to make sure that different processes agree. And if they don't agree, we need to understand why the differences may arise. And we go step by step to establishing distances from the nearest to the furthest objects. Whatever the measure of distance we use, whether it's kilometers or parsecs or megaparsecs, which we will sort of define more formally today, although we have used these terms as 1 parsec equal to 3.26 light years earlier, the basic measure right now is the meter. So do any of you know how a meter is defined now? How is a meter defined?
It's defined as a fraction of this, the distance light travels in a second.
Very good, excellent. That is today's definition of a meter, right? Now, to actually just thought it may be interesting just to learn a little bit of the history of how a meter is defined. In fact, this happened very early on when the scientific revolution was also on, and France was at its peak. This is the Napoleonic era. And that was a time when they tried to define the meter as 1/10 millionth part of 1/2 of a meridian. And the meridian measured from the equator to the pole and passing through Paris. Okay, so that was how it was defined, and that was trying to make it more concrete in terms of the earlier prevailing things of distance measurements or length measurements of, distance from a king's thumb to his nose, which are obviously had no sort of rigor to it at all. But it's soon involved into trying to make a prototype, and that was a platinum bar which was used, and later iridium was put to it to make it a bit stronger, and then we moved on to defining it in terms of a specified transition of krypton. This was as early as 1960s, and today, as you all mentioned, that the length of path traveled by light in vacuum of a second is what is referred to as the meter. Okay, so it's interesting the way the accuracy has evolved in terms of measuring the meter as well, and these were the relative uncertainties or the uncertainties over at different periods which have been marked over here. This has been reproduced in Wikipedia from a book by Francois Cardarelli, and it's sort of interesting to see how accuracy, even as basic a measurement as a meter, has evolved in the last couple of 100 years or so. Now, you've already seen that when you come to measurements, we talk about measurements starting from the Earth today. And this is something which we discussed and met earlier about how Aristarchus measured the radius of the Earth, okay, from the size of the Earth using geometry and measurements. And the Earth was believed to be a sphere. Pythagoras argued it more from aesthetic grounds. Aristotle put it on a more sort of logical arguments of lunar eclipses, the shapes that you see, and also how visibility of stars from the south and the north vary, because you will not see stars below a horizon in case of a circular or spherical Earth. And this is something you'd have learned in your elementary geography as well, how when you see a ship going over the horizon, you see the top of the mast till the end. So this was some of the early measurements of trying to measure the size of the Earth. And they were not bad, actually. You can see that this is Eratosthenes' measurements, if translated into modern measurements of kilometers. And these are modern satellite measurements. You know that the equatorial radius is slightly larger than the polar radius, and that is reflected over here. And this is about the average radius of the Earth. So this was one of the very early measurements of celestial objects. But the Greeks actually did not confine it to just measurements of the Earth. They tried to find out measurements of the distance to the moon. And they had simple geometrical arguments to show how many times it may be larger. In fact, in the size of the moon relative to the Earth, size of the sun, relative size of the sun, relative distances. So it's quite interesting to look at the historical development of the field. I will just pick up one or two examples over here because we are short of time. Now, suppose, for example, you look at an eclipse, okay? You look at an eclipse, and the sun is a large body. It's not a point, and it's not too far away. So the rays will actually converge. If it was a very parallel beam of light, you'd get a cylindrical kind of pattern over here. But let's assume that this is straight for a moment. You could still find out the maximum duration of an eclipse because the velocity of the moon would be given by twice the radius, because that is the time, assuming it is parallel, that it will take to cross the dark region, the duration of the eclipse, and you can time the duration of the eclipse, and you'll get the velocity of the moon. And you can also calculate the velocity of the moon from its orbit around the Earth, okay? The period of the moon orbiting the Earth, and you can go and put the distance 2 pi, the Earth-Moon distance, that is the radius 2 pi r, divided by the orbital period of the moon around the Earth. And equating these two velocities, you can get a relative distance for the Earth and the moon in terms of the radius of the Earth. And radius of the Earth, Aristarchus had determined it from the shadow which it casts in Alexandria when it was overhead in Sion. And from that measurement, you can go and calculate what the Earth-Moon distance is. And the values they got were not bad again. I've just written down the modern values over here, which is 384,400 kilometers. And this is the radius of the Earth. And DEM upon RE is about 60.3. And from just a crude argument over here, somewhat crude, but you can see that, you're not hugely off. And considering that, this was done more than 2,000 years ago, one has to appreciate the ingenuity and the observations of the ancient astronomers. Triangulation was attempted by Ptolemy to the moon, and he arrived at a distance of about 390,000 kilometers. Hipparchus also made an attempt at triangulation, which is much before Ptolemy's time. Okay, and today the most sort of accurate methods that we get is by laser ranging, and this figure on the right just illustrates that. You can read much more about all these from the references which I've listed below, and I'm sure if you search the web, you will actually probably find even better references than what I've given over here. And this one, the radar ranging started, one of the early attempts was in the late 50s. This is the Royal Radar Establishment. After the war, people, they developed the radar technology to a large extent during the Second World War, and that was put to good use. Radio astronomy developed after that. And this was one of the early radar ranging experiments which established the distance to the moon to an accuracy of about 1.25 kilometers. Apollo 11 laser ranging, they had left a reflector, and the instantaneous accuracy is at a millimeter level. So the moon is also in an elliptical orbit. Okay, I've written down an average distance over there. There is a perigee and an apogee, which have been listed over here. Now, this was the distance to the moon. So parallax attempts, these are triangulation methods. So, and for these distances, one need not have to worry very much about general relativistic effects. Cassini actually attempted triangulation of Mars in 1672-73. And he had sent one of his fellow astronomers, Jean Richer, to French Guiana, and took measurements at the distance of closest approach of Mars, and arrived at, again, not unreasonable values, given that, the technology available at the time. In fact, even to keep accurate timekeeping, they had looked at the phases or the moons of Jupiter, and they observed parallax against the background of stars. And here, while mentioning about parallax, it's also probably worth mentioning that Aristotle and even Tycho Brahe, many hundreds of years later, argued against a heliocentric universe, because they said that if the Earth is moving around the sun, then one should be able to observe parallaxes of the stars. But they did not realize, neither did Aristotle and Tycho Brahe, realized that the stars were so much further away that the parallax which they expected would be extremely small to register. So I'll leave it to you as an exercise to look at how the transit of Venus has also been used to estimate distances. And there's quite a nice article which I came across, which I've given a link to, where some of the maths has been derived. And you can also perhaps find other references as well. But today's modern method of determining distances to the planets, at least nearby planets, has been through laser ranging. So in fact, the radar, the Arecibo telescope, while it existed, had a very powerful radar as well, which was used for a lot of atmospheric work and some other kind of work as well. Now, for example, over here in a diagram of beam bouncing off Venus is being shown, and you can see that once you make these measurements at the maximum elongation, you have a right angle triangle. And if you know the angle over here, you know the distance from here. You can also measure the astronomical unit distance between the Earth and the Sun, as well as between the Venus and the Sun. Now, once you have measured the distances to one of the planets, then you had very detailed and accurate observations of planetary motion. And applying Kepler's laws, you could go and determine the distances to all the planets. I've just listed over here the distance, what 1 astronomical unit is, just for completeness, but you're familiar with this. 1 astronomical units is roughly, it's difficult to remember all these digits, but roughly about 150 million kilometers is something one could remember. And then you can see that the ones which are the inner planets, Mercury and Venus, and then you go outwards further and further away to Uranus and Neptune, which is close to about 30 astronomical units. I've also written down the Earth-Sun distance, which is, again, an easy number to remember. It's about 500 seconds. And you can also estimate the Earth's orbital velocity. And it's actually quite a large number, right? I mean, when we write it as 30 kilometers per second, we don't think very much about it, may or may not think very much about it. But when you put it at kilometers per hour, something which we are more familiar with in terms of speeds of vehicles, it's a whopping 107,000 kilometers per hour or so. So we are really zipping around in space without being conscious about it. Just a quick revision and a recap. Most of you maybe would be familiar with this, but just for completeness, that a parsec, as we go further away, we need to, we can observe parallaxes of more distant objects by modern sort of more accurate measurements, and particularly from satellites. But the basic definition of a parsec is given by trying to find the parallax angle as the Earth rotated around the Sun. You can see that D is equal to 1 AU, which is the average distance between the Sun and the Earth, and divide tan P, the parallax angle would be given by 1 AU divided by D. So D is equal to 1 AU divided by tan P, which is 1 AU. Tan theta is on the order of theta for small angles. So 1 upon P, astronomical units. Now, 1 radian is equal to so many degrees. So if I put the angle in degrees, I will get in degrees or arc seconds. I will get D is equal to 206,264.806 divided by P in arc seconds, and this will be so many astronomical units. Now, if I define this to be a parsec, then I put this 1 over here, so that when I have a parallax of 1 arc second, I have a distance of 1 parsec. So that means that this number over here would be what is expressed as a parsec, okay? Which is 3.0856, if you translate into meters, into 10 to the power of 16 meters, is defined as a parsec. And 1 astronomical unit, again, if you want to put it in terms of meters, it's 1.496 into 10 to the power of 11 meters. But as long as you remember it as about 150 million kilometers, it should be fine. And 1 parsec is 3.26 light years. So this is the basic way that a parsec is defined. Now, so if I can measure the parallax, I automatically know the distance in parsec, okay? So the goal is to try and determine the parallax of objects. And the parallax, as I mentioned, is an extremely small angle. So the technological challenge is in terms of trying to measure that angle. You can see over here that further an object is, the smaller would be the parallax angle that you're going to observe. So how far can you push it? So parallax comes from, parsec comes from parallax second, parsec. Now, Proxima Centauri is the nearest star. Okay, it's part of the Alpha Centauri complex, and the parallax over there is less than an arc second, 0.768 arc second. And you remember we talked about typical seeing conditions on a good side is about 0.4 arc seconds or so. So, but this parallax puts it at a distance of 1.30 parsec, and that is 4.24 light years. So Proxima Centauri is the nearest star. It is part of the Alpha Centauri complex. Alpha Centauri is slightly further than Proxima Centauri. One of the first heroic attempts, there were attempts to measure parallax for much before Bessel did it. This is the same Bessel as of the famous Bessel function. Frederick Bessel did it in 1838, and he painstakingly took observations over a 4-year period, and the early results actually did not yield reliable values, and he later determined a parallax of 61 Cygni, and this was quite a heroic feat. And 61 Cygni is a star in the Cygnus constellation. It's somewhere near where I'm putting the cursor over here. This was okay, and from that distance, he determined the distance to be about 3.16 parsec, which is 10.3 light years. And from more modern measurements with the Hipparcos satellite, the distance is about 11.4 light years. So you can see Frederick Bessel in 1838 did a pretty good job in trying to determine the distance to the star 61 Cygni. It's a visual binary with an orbit of about 659 days. So to measure distances from triangulation, one needs to be able to measure parallax angles more and more accurately. Okay. So now when we come to the Hubble Space Telescope, we can observe with better resolution because we are not affected by the seeing conditions in the atmosphere, and so Hubble Space Telescope measured the distance to globular cluster 6397 and estimated a distance of 7,800 light years. Now, Hipparcos was a satellite mission, which was specifically one of the main targets was to measure parallax. Hipparcos, it sounds like Hipparchus from ancient Greek astronomers, but it also stands for High Precision Parallax Collecting Satellite. Okay, it was deliberately sort of made to sound similar, and it measured the parallax of about 120,000 stars with an accuracy of about 1 milli-arcsecond. So you can see that with satellite measurements and a dedicated mission, Hipparcos, that we have pushed the distance measurements by triangulation to a very large number of stars to greater distances than was possible earlier. They measured for another 2.5 million stars, but with a lesser degree of accuracy than 1 milli-arcseconds. Hubble Space Telescope, as I just mentioned, for a particular globular cluster, it extended the measurements to even sort of larger distances. The next major advances actually came with Gaia, which is a space-based telescope launched in December 2013, and the objective is to observe 1 billion stars to micro-arcsecond accuracies levels. So that is going to actually really revolutionize not only distant measurements, but also a detailed 3-dimensional map of our galaxy. And a lot of exciting results are coming out of Gaia, and I'm sure it will continue to do so for the near future. So the objective is to try and get these parallax angles, because here you're just based on geometry. You're not worried about the intrinsic property of a source, because it's very difficult to get an absolutely rock solid intrinsic property which is absolutely the same for all objects. There would be some scatter. Then you'll also have to deal with calibration. You'll have to deal with, for example, interstellar reddening or absorption or scattering of light as it comes towards you if you're using a standard candle. And if you're using a standard rod, you'll have to worry about projection effects. For example, a rod is not always inclined at 90 degrees to the line of sight that you get the upper limit, but it will be inclined randomly towards you. For example, all the double lobe radio galaxies are randomly inclined at all angles to the line of sight towards you. So the most solid way of measuring distances, at least for the nearby universe, is by triangulation, is by geometrical methods, parallax. So far, I mentioned largely about, or almost entirely about optical observations, but you can also do parallax using data at other wavelengths. And here is what I have shown is with radio observations. But of course, you need very high resolution observations. You remember Gaia is talking about micro arcsecond resolution. So you need micro arcsecond resolution. Hipparchus was talking about milli-arcsecond resolution. So you need that kind of resolution to be able to determine the angles very accurately and small angles so that you can push the limits of measurement of distance by geometrical methods or triangulation or parallax to objects which are further and further away from you. Here is an example of using the very long baseline array, which we met earlier while talking about the radio window of the universe. And as you remember, resolution is given by lambda by t, and the very long baseline array has antennas spread out across not only across the US mainland, but also to Hawaii. And this is the results from a particular star called T Tau Tauri, SP, a companion of a well-known young stellar object called T Tauri. Now, the VLBA parallax determined a distance of 146 or 147 parsecs. Hipparchus did slightly differently. The errors are a bit large over here, so within the errors, they would be okay. But these are the kind of consistency arguments that one tries to deal with in terms of measuring distances of objects. Now, the other thing I should mention over here that while trying to measure parallax of objects, we have so far assumed that the object is fixed and the motion is due to, the angle is due to the Earth's motion around the sun. But the object itself could be moving. For example, if it's in a binary system, the object itself could be actually rotating about the center of mass of the object. So one has to model out the proper motion of the object as well. It could be moving, the star itself could be moving. So here they have measured the positions of the objects which are marked in red from VLBA observations. And what is also shown is the best fit expectation of the position of the star given both parallax and proper motion of the objects. So this is something which one has to factor in as well while trying to determine distances. So you can see that we are going to larger and larger distances as we are going to extend the accuracy with which we can measure the parallax angles, not only accuracy, but how small a value that we can measure. But beyond a certain range, it becomes extremely difficult. So one of the early methods which was developed to go to the next step, which I've called step 4 over here, is what is called the moving cluster method. What is the moving cluster method? We talked about star clusters, we talked about open clusters and globular clusters. Now let's think of open clusters which are in the plane of our galaxy. Okay, this is a gravitationally bound system. The outer members may be more loosely bound, but they form roughly around the same time. And due to the overall dynamics of the galaxy, the movement of the galaxy, the rotation of the galaxy, these stars will also appear to be moving away from you. Moving together could be sometimes star clusters could be moving closer towards you or away from you. But let's for argument's sake over here, let's consider a cluster which is moving away from you. Now the cluster has many members, and just as you would see, for example, if you had cars going in parallel along a multi-lane highway, they would all try to converge to a point. So the stars moving with a certain velocity in a certain direction will also appear to converge towards a point. And because the star appears to be moving, there'll be two components to it. One is the radial velocity, and the other is the tangential velocity. And that is what is illustrated in this figure over here, that if it is moving at a certain velocity v, that it'll have two components. One is the radial velocity, which is moving away from you, and the other is the tangential velocity, which is orthogonal towards you. Okay, and because it is moving in the sky plane, which is orthogonal to you, it'll have a certain proper motion, which is given by mu over here, which is the angular distance it has traveled divided by the time over which you have made the measurements, and you can put it in terms of arc second per year, and that would be the proper motion of the object. Okay. Now you can do a little bit of algebra, but this figure is just to illustrate to you about how the stars maybe all appear to converge in a particular direction, making an angle phi with your line of sight. Okay. Now let's look at the little bit of algebra that we will do to try and get an expression for how we get the distance. The proper motion, as we mentioned, is mu is equal to theta upon t. Now theta you can relate it to terms of the velocity at which it is moving and velocity at which it is velocity which is moving by taking that, it'll traverse a distance d, or distance capital D or R, whatever you want to call it, and that will be related to that can be related to this distance d and the velocity at which is moving out. You can play around with it a little bit and you'll get an expression of mu can be expressed as a transverse velocity divided by the distance. Okay. Now we talked about the velocity in a particular direction having a radial component and a transverse component. So the radial component is something which you can measure from the Doppler shift of the lines, okay, of the lines. So that will give you the radial velocity, which is v cosine phi, and the transverse velocity, which is v sine phi, you can measure from the proper motion measurements. And you can relate Vt and Vr by this relation over here. You can plug it in over here and get a relation between the radial velocity, between the distance of the object, the radial velocity, the angle at which it appears to converge, and the proper motion. Okay. And you can measure this for a whole range of stars of that particular cluster, and also measure the proper motions of that particular cluster, and plug these values in, and you'll get a distance to the cluster. So this was a clever way of trying to estimate distances, still a better geometry, but it also involves measurements of Doppler velocities and proper motions of objects. Okay. And this was used, this is what is called the moving cluster method. And this was done in great detail to the high-risk cluster. This was the next major step from measurements with parallax and triangulation. And this became a standard for quite some time. It was important to get the distance to high-risk cluster as accurately as possible. So these are some of the more recent measurements, which I put over here, that this is a work by Perryman et al. In 1998, which determined about 46.34 parsecs. This is from the Hipparchus 2 data, Van Leeuwen 46.45, and the Gaia Calibration, which you mentioned, 2017, 46.75. Okay, so you can see that this moving cluster method provides another important way of trying to measure distances, and obviously with more later space missions like Hipparchus and Gaia, you could try and validate and check what you have got from the moving cluster method as well. So these have been Gaia measurements and Hipparchus measurements. You can see that these are well within the ranges of what they can measure by triangulation or parallax methods. So these provides a check of the different rungs so that you're not entirely reliant on just one method, but you can keep checking to make sure that you get consistent answers as you move up, measuring distances of further and further objects using innovative techniques over here. And sometimes things don't all check. For example, this is the moving cluster method applied to the Pleiades cluster, has also been applied over there. And then this is a summary which I took of Pleiades measurements of done by a variety of authors and using different methods as well. Okay. And you can see that a lot of it actually is in the ballpark of about 130 to 140 parsecs. But for some reason, Hipparchus gives you a slightly lower value. And these are aspects which one tries to understand to try and get a more complete picture to make sure that our distance scales are as robust as it can be. Now, in a moving cluster method, there are possible sources of error which can come in. Star clusters are assumed to be just moving in one particular direction, not expanding or contracting or rotating, assumed to have minimal or not much of random motion. Stars are generally assumed to have a similar velocity. One does take an average. One can take as many stars as possible to reduce these errors, but you are also prone to some contamination by non-cluster members as well. But you can still see that they give reasonably good answers, as one can get by comparing these with the more recent measurements of Gaia and Hipparchus as well, which relies on triangulation. So the next major sort of step, which I've called step 5, is called spectroscopic parallax. But it doesn't really have to do with parallax the way we have talked about it. Now, you're familiar with the Hertzsprung-Russell diagram. One of you gave a very nice talk on it as well. Now, when I take a spectrum of a star, which is, as you know, as we have discussed briefly, but we look at it in more detail, the stars are characterized by absorption lines. And from the nature of the lines that you observe, you can decide on the spectral type. You can also decide on other properties on the surface of the star. Now, for example, suppose I had a calibrated Hertzsprung-Russell diagram. Here is given on luminosity versus the color. Or this can also be the spectral type of the star, which we will also discuss a bit more when we discuss stars. But as an example, for example, let's take a G2 star over here. And this is calibrated in terms of absolute luminosity, denoted by absolute magnitude over here, which we will discuss a bit later. Now, if I know the apparent flux or what I observe, and I know the absolute luminosity from the kind of star that I'm looking at, then I should be able to measure the distance of the object. For example, from the spectra of the star, if I have a G2 star, okay, that if it is a main sequence star, I know that its absolute luminosity should be in this range. There's a bit of a scatter, but it's still pretty tight. And from the observed flux, I can go and estimate the distance. But there is one little catch to it, that if you look at the Hertzsprung-Russell diagram, it is not just a main sequence, but it is also stars at other locations which have the same spectral classifications. These are what are known as the giants and the supergiant stars. So it's not just the spectral type that I need to classify of the star, but I also need to know the luminosity class. We'll discuss a little bit more about luminosity classes when we discuss stars, but right now it is adequate to know that, that even for the same spectral signature, you can have stars which are in the main sequence, which may be giants, which may be supergiants, and we need to know the different classifications of giants, supergiants, the luminosity classification as it is called, in addition to the spectral classification, to be able to know the absolute luminosity of the object. And once you know the absolute luminosity, then from a measurement of the observed flux, you can go and determine what the distance to the object is. So this just gives you, elaborates a little bit more on what I've already said, that we need to know the luminosity class as well in order to estimate the distance. So you note the position in the HR diagram, you look at the luminosity and the spectral classification, you compare it with the HR diagram, which has been calibrated for absolute luminosity, and then you straight away get the distance to the object. Lines also give other information as well. For example, the weight of the lines, it will give you information on the surface gravity of the star. So the spectra of stars contain a lot of valuable information. But to initially establish this main sequence over here, okay, to calibrate it in an absolute way, I do need to know the distance by some other means. So parallax has been the gold standard of distances. It relies on geometry, and there is no other assumption over here. Okay. So once you have a calibrated HR diagram using distances such as parallax, then you can use what is called spectroscopic parallax, but it's not really parallax in the sense that we have discussed. Now, rather than looking at it for a single star, you could actually, for example, if you had a cluster of stars, you could plot the entire main sequence for it. Okay, you could plot the main sequence for it, and then see how much the whole shift is. So for a single star, you may be prone to more uncertainties, but if you had a cluster and compare the HR diagram for the entire cluster with a calibrated HR diagram in terms of absolute luminosity and spectral type or color or temperature, then again you get the distance for the entire cluster. So if you fit it for many stars, you're generally more reliable than being prone to uncertainties due to a single star, but it can still be reliably used. One of the aspects which one is to bear in mind while doing these spectral fitting or the luminosity, sort of estimating the luminosity classes and measuring distances, is to be aware of the effects of the interstellar medium. So you have to be aware of the importance of interstellar extinction, and there are pretty detailed maps of reddening or the degree of extinction towards different directions in the galaxy, and recognition that there was something in between. In hindsight today, we know that William Herschel reported regions in the sky with no stars. Bernard in the early 20th century had at last selected regions of the Milky Way, many regions with no stars. Here is one of Bernard's objects. And Trumpler was really who worked extensively on trying to put this on a framework and understand the effects of extinction. That was again in the early half of the 20th century. So this is something which you have to bear in mind, but we will not discuss too much over here in detail. Maybe perhaps if there is time later, we will discuss, but scattering and absorption are both important, and interstellar dust grains are what plays a very prominent role. Again, there is much more of smaller grains, so extinction is more important at shorter wavelengths, and that is not very different for what you see when you look at scattering of sunlight by the atmosphere, that the blue light gets scattered much more than the red light. So extinction over a large region can be sort of described as extinction varying as 1 upon the wavelength. There are peaks due to specific features, grains, silicate grains, but roughly over a large range, it can be denoted by 1 upon lambda. And it depends on direction in the Milky Way. And it also could be different for different galaxies. And for external galaxies, it will also depend on the way the galaxy is inclined towards you. Because if you see it edge on, the stars on the further side will suffer far more extinction than the ones which are on the surface. So that was about main sequence fitting and spectroscopic parallax. The next major step, which I've called run 6, comes from the period luminosity relationship. And this is again something which you'll talked about. So I'm going to go through it rather rapidly. This was due to the pioneering efforts of Henrietta Leavitt, who was looking at stars in the Magellanic Clouds. And she found lots of variable stars, but a small fraction seemed to be regular variables and varied very periodically. And she noticed that those which were brighter had longer periods. And all the stars in the large Magellanic Cloud or the small Magellanic Cloud would be at a similar distance. So she also realized that this must be related to the intrinsic luminosity of the object, but that had to wait till one determined distances independently. But the discovery of the brightness of the object and the periodicity of these Cepheid variables is something which Henrietta Leavitt had established. This is just a light curve of a particular Cepheid variable, and you can see that the light curves also vary for the different kinds of Cepheids, but it is extremely regular over here. Okay, and stars pulsate in this fashion. Sometime during the late stages of their evolution, they expand and contract. You can measure the expansion and contraction from the Doppler shifts of the lines, and you can, but this also leads to changes in the luminosity, a very periodic change in the luminosity object. And from these relationships of luminosity and period, one can go and estimate what the distances are. Now you can see that there are two types of Cepheids which are mentioned over here. Type 1 are the classical Cepheids. Type 2 are what are known as the W Virginis type or type 2 Cepheids. And there is another kind of stars over here which are also variable, which are called the RR Lyrae stars. The Cepheids were named after the first known object on this class called Delta Cephei. Delta Cephei is towards the constellation Cephei. And astronomers have had a not very homogeneous way or a standard way of putting names. So you'll find a variety of different kinds of ways that stars have been named. Delta Cephei would be, it would not be the brightest, for example, alpha, beta, gamma, etc. But later one went on to putting numbers when you could not really accommodate names with the letters of the Greek alphabet. Things have become more standardized now when one uses more of the positions of these objects, which have been determined accurately, although these classical names historically continue to be very, very widely used. In stars, you'll also come across names with BD in it, which is a very extensive catalog which was compiled by the Bonn Observatory many, many years ago. Okay, but you can see that for these two types of Cepheids, there is a difference. So if you did not distinguish between these two, did not realize that there were two different types of Cepheids, then you'd have a larger scatter and your errors in the distance measurement would be accordingly higher. So these curves also vary in their light curves, but basically type 1 Cepheids, which are known as the classical Cepheids, are high metallicity objects and they're generally population 1 objects, whereas the type 2 Cepheids are lower metallicity and they could be population 2 objects. The recognition of these two types of Cepheids came pretty early on, 1937, 1940, the work of Joy. Henrietta Leavitt's observations were in the early part of the 20th century. 1908, I think, is when she published some of her initial results. So RR Lyrae stars are also pulsating variable stars. It's not as steep as this kind of period luminosity relationship which you see for Cepheids. They are less luminous than Cepheids. You can see over here, these are luminosity given in terms of solar luminosity. You can see Cepheids are normally much more luminous than the RR Lyrae stars over here. This is about 100 times more luminous than the sun. And these are also, the RR Lyrae stars are also population 2 objects. They're found in globular clusters, bulge and halo of the Milky Way. Their periods, you can see, are usually less than about a day. So they're much shorter periods than that of the Cepheids. And their luminosity, you can see from the nearly flat region over here, that that you can almost take it to be a constant to at least get a first order estimate of the distance. So once this Cepheid period luminosity relationship was established, one needed to just find Cepheids in more and more distant galaxies and objects. And once you know the observed flux of the Cepheid, then you automatically know the distance because you know what the intrinsic luminosity should be given the period of the Cepheid variable. So Harlow Shepley, director of the Harvard College Observatory, used a large sample of Cepheids, determined distances to the small Magellanic Cloud, globular clusters, And he also found that some of the bright globular clusters are very bright stars. And he used the brightest stars to see how far he could extend this. And this way, by looking at globular clusters, measurements of distance to globular clusters, which, as you know, are more spherically distributed compared to the disk of the galaxy, one began to understand how the different components that make up the Milky Way, our galaxy, are distributed as well. And one could use these to try and estimate the size of our galaxy. And so the discovery of the period luminosity relationship by Henrietta Leavitt heralded a very important step in our distance measurements of the universe. Edwin Hubble, whom we have met earlier, Hubble's expansion of the universe, the Hubble-Lemaître law, he identified Cepheids in the Andromeda Nebula and the Triangulum Nebula. And while the debate was still on earlier whether these were island universes like our own, as Immanuel Kant described it many years ago, was established without any doubt once you could identify Cepheids in these galaxies and discover their distances and find that they far exceed what is the known size of our galaxy. So these established that these spiral nebulae were indeed galaxies. And of course, he went on to discover the expansion of the universe by, once you know the distance and you know the redshift of this object, one could show that, or he showed that the further away an object is, the higher the velocity of recession. So these were just pictures of some of the galaxies where Cepheids were identified, and from a calibration of the luminosity period relationship, the distances could be extended using the period luminosity relationship to further and further galaxies. So and this continues to be one of the very important areas of research. You can see over here that with the Hubble Space Telescope, one of the key projects has been refining the extragalactic distance scale by observing Cepheids in more distant galaxies. So many new Cepheids were found, for example, in the spiral galaxy M81, which extends it now to distances of not just kiloparsecs, but now we are going to the megaparsec scale distances. And one of the more distant stars, Cepheids which have been identified, is in the galaxy M100. This is an image of the galaxy Messier 100 on the left-hand side. And on the right shows one of the Cepheids which was found by the HST and which is monitored. And from the monitoring of the Cepheid, now we can see that we are going to close to about 20 megaparsecs or so. So we are going further and further away as we are getting higher and higher in the distance rung ladder. Now, variable stars, Cepheids and Lyrae, there are advantages and disadvantages. Cepheids are bright, easy to find, but brighter objects are also rarer. So relatively rare, and period may depend on metallicity, color. There's subtle things which one needs to calibrate well. The population one object in the disk of the galaxy. So effects of extinction are aspects which you have to bear in mind while trying to do the calibration and getting the absolute luminosity. Lyrae stars are population 2 objects. There's less dust. They're easy to find. There's less extinction, but they're less luminous than Cepheids. So because they're less luminous, you can see that the highest luminous object are at least a couple of orders more luminous than the Lyrae stars. So you're confined to smaller distances compared to what you can do with Lyrae stars. Now, measuring distances, as we just mentioned, led to what we today call the Hubble-Lemaître law of the expansion of the universe. Weston Slipher actually found that the spectra of spiral nebulae were redshifted for almost all. This was well before the work of Hubble and Lemaître. And Lemaître, based on GTR, worked out models of the universe and used existing observations. And Hubble established a rough proportion between redshift and distance, something that you're all familiar with, which we have met earlier. And this is what I have now called the next rung of the cosmic distance ladder. So now, once you calibrate that with Cepheids, and you can use this redshift of the object by how much a a galaxy is redshifted out to measure the estimated distance of the object. So all you need now is a spectrum of the object. In all these discussions, I've not been exhaustive in terms of the different ways of measuring distances, and that is something which I would like you to bear in mind. Okay, this is just another illustration of the Hubble-Lemaître law, and this is just sort of blown up over here a little bit to show you that that in a cluster, when you estimate velocities for a cluster of galaxies, that in addition to the velocities due to the overall expansion of the universe, that there will also be random velocities of the galaxies themselves. They're moving around in the potential well of the cluster. So there, for each of these objects, there will be a scatter in addition to the overall expansion of the universe. When the objects are very close by, then you might find that the peculiar velocities may even be larger than the overall expansion of the universe, as we find that Andromeda is coming towards us, although the overall universe is expanding. But as you go further and further away, the random component is a small fraction of the overall velocity inferred from expansion of the universe. Now we'll go for another standard candle, and this would be the last aspect which I will mention in terms of distance measurements. Now, if we had a very luminous standard candle, after all, we saw that even for 20 megaparsecs, you are pushing it with the Hubble Space Telescope. So can we have a more luminous standard candle than what has been possible so far? Now, as we know that some of the brightest objects in the sky, which we met, were when massive stars or stars explode in the end stages of their lives as supernovae. And these are extremely bright objects and can be seen to large distances. But the question is, are they a good standard candle? For example, if it has to be a good standard candle, then the dispersion in the luminosity has to be absolutely minimal, so that you can tell yourself, hey, this is the intrinsic luminosity, and this is my observed flux, so this is the distance to the object. Now, there are different kinds of supernovae. I will just talk about two types over here. One is a type called type 1a. These different classifications of supernovae are based on the spectra and light curves of the supernovae. And type 1a is when a carbon-oxygen white dwarf accreting material from its companion detonates when it exceeds the Chandrasekhar mass limit, and it has a maximum brightness MV of about minus 19.3 absolute magnitude. We'll come to absolute and operant magnitude in a short while. And these could be good standard candles. Okay, there is a diversity of light curves, but one has to see if those can be standardized or if there is any way one can understand that. The type 2 actually leaves behind a compact object like a neutron star, for example, or a black hole. But what happens is that there is a reasonably wide dispersion in the luminosity. So this type 2 actually don't provide us with being a good standard candle. If you look at the type 1a supernovae, okay, it can be characterized by its unique spectrum and its light curve in various stages, as we saw when we were talking about gamma ray astronomy, can be described by the decay of radioactive species, which get synthesized during the explosive stages of the star. But these are just an illustration of different kinds of type 1a supernovae which go off. Now you can see that there is a very wide dispersion over here. This is 10 to the power of 10 over here. This is 10 to the power of 11. So about an order of magnitude or even less than that. But you can see that there is a pretty large dispersion over here. But what people realize is that the brighter ones appear to fade more slowly, whereas the fainter ones appear to faint more rapidly. So this is what is often referred to as a stretch factor. And if you correct for that, okay, if you correct for that and allow for that and get it to, then you have a light curve which can provide a very standard candle. Okay. And today, because these objects are extremely luminous, you've been able to measure distances to very high redshifts. So this is what I illustrated to you by the stretch factor.
Correct for that. How do you correct for that?
You find out how the magnitude is changing with time. For example, you can see by what level it is changing, and you standardize that to a fixed value. Okay. So, for example, you can see over here that the drop in brightness over here is slower than the drop in brightness over here. So you measure the drop in brightness with time and standardize it to a fixed set of values which you agree upon. So this is the work which has been. So, I mean, I picked up these figures from one set of papers, but there are many sort of persons who have done this standardization to try and get the accurate standard sort of light curve by taking care of this stretch factor. Now, once you do that, you have distances which have been measured to pretty high redshifts as well. And that forms the last rung of the distance ladder, which I've tried to sort of summarize in terms of measurements of distances of celestial objects. But as I mentioned over here, that I have not been exhaustive in terms of the different ways of estimating distances. And people have used a lot of other distances as well. In fact, Ned Wright himself has a number of articles which are available in the web talking in more detail. So if you want more detail, you can talk about it. But perhaps without illustration, I can just mention one aspect of it. You know that galaxies are rotating, spiral galaxies are rotating. And the velocity at which it is rotating is related to the luminosity of the object. If you remember, when we were talking about H1 observations in the radio window, neutral atomic hydrogen, that the profiles of the hydrogen emission, you had things which were coming towards us and going away from you. One side of the galaxy would be coming towards you, the other side of the galaxy would be going away from you. And you can see how fast the galaxy is rotating by the difference in the velocities of the ones coming towards you and going away from you. And how rapidly it is rotating is related to the luminosity of the galaxy. So if you took a spectrum of the galaxy, even a single dish spectrum of atomic hydrogen, then you will find that you can go and calculate the luminosity of the object by looking at the H1 spectra. So all you need is to take an H1 spectrum. The H1 spectrum will tell you how fast it is rotating. And from that velocity, you can estimate what its intrinsic luminosity is. And once you know its intrinsic luminosity from the observed apparent flux, you can go and calculate what its distance is. So you can see that there are various checks that one uses as one goes along. And today, with an estimate of the Hubble's constant from a number of ways of doing it, we believe reasonably accurate estimates to distances even in the furthest reaches of the universe.